Here we have a wedge of mass big M and angle theta. The surface of this incline is perfectly smooth. The wedge rests on a perfectly smooth horizontal surface, and it is not fixed, so it's free to move horizontally. We have no forces preventing it from moving horizontally. Our wedge is initially at rest. Suppose we place a particle of mass little m on the wedge. Well, that means that we have applied a force on the wedge, a contact force on the wedge due to the particle. That force is perpendicular to the surface of contact. So it's in this direction. Let's suppose that the magnitude of this force is r. Let's look at the other forces acting on the wedge. Well, we have its weight, which is vertically down, of course. I can show this weight vector anywhere. Well, we could put it at the center of gravity, but I'll just put it here. The weight, of course, is big M times g. Now, since the y component of the acceleration of the wedge is 0, in other words, the wedge does not move in the vertical direction, by Newton's second law, the y component of the resultant force on the wedge is also 0. Okay, this is just mass times ay, where ay is 0. So let's get the y components of the forces. Well, what about the y component of r? Well, that's pointing vertically down, as you can see. We also have horizontal component that's pointing to the right. So we see we have these two vertical vectors pointing down, so they must be counterbalanced by an upwards force. So the upwards force must equal in magnitude to the sum of these two downwards vectors. So it might look like this. Let's call this force N. Okay, so what is this component of r? Well, the angle in here is theta. It's the same as this angle here, because we have an angle between a pair of lines here which are perpendicular to this pair of lines. So the angle between both pairs of lines is the same. So for the y component of vector r, we just multiply r by cos theta. Okay, the y component is adjacent to theta. So if we take upwards as positive, the y component of the resultant force is n minus r cos theta minus big M times g. So if we want to calculate the force on the wedge due to the horizontal surface, that is n, we have to calculate this quantity here. So we are given big M, but we don't know what big R is. Now let's look at the horizontal or x component of the resultant force F on the wedge. Well, we can see that n and mg have no horizontal or x component, but r certainly does. Okay, the x component of vector r is opposite angle theta, so its magnitude is r, that's the hypotenuse, multiplied by sine of theta. So here we have to sum all the x components. Well, we only have one x component. It's r sine theta. Okay, we saw that we had no y component, f sub y is 0, so we only have an x component. So this is actually the resultant force, so we can drop this x. We know by Newton's second law that the resultant force on something is its mass, which is big M for the wedge, times its acceleration. So that means the acceleration is obviously to the right. So you see here we have an equation with two unknowns, r and a. Next we will look at the forces on the particle. Well, we have a force on the wedge due to the particle of magnitude r, so by Newton's third law we have an equal but opposite force on the particle due to the wedge. So this vector also has magnitude r. Okay, the other force on the particle is of course its weight, which is little m times g. Now, these are the only two forces on the particle. We are assuming no friction in this problem. We will refer the motion of this particle to a fixed set of xy axes, where the positive x-axis points down the incline and the positive y-axis points into the incline. Now with this convention for our xy axes, the calculations will be simpler, because the acceleration of this particle is not entirely in the x direction, as it was for the case of a fixed wedge. So sometime later the particle doesn't just end up over here. Remember, the wedge has moved to the right, it's accelerated to the right. So after this particle has been moving for some time, it might end up, say, down here. And the wedge has moved some distance to the right. So the acceleration of the particle is not entirely in the x direction. It's more like in this direction. So it's got a positive x and a positive y component. Let's call the acceleration of the particle b, and I'll mark in both its components. I'll call the x component b sub x and the y component b sub y. You can see with our convention for our xy axes, both bx and by are positive. Now let's consider the resultant force on the particle. We know from Newton's second law that the resultant force is the mass of the particle m multiplied by vector b. So the resultant force is in the same direction as vector b. Okay, so that's the sum of these two red arrows. It's not drawn to scale, as you can see. We're going to look at the x and y components of this resultant force. So let's start with the x component. So I let capital F be the resultant force on the particle now, and F sub x is the x component of that resultant force. We can see that R has no x component, but the weight mg does have an x component. Okay, it's the side opposite theta in this right angle triangle, and it's given by mg sine theta. So here we have the same situation as for a fixed wedge that we covered in a previous video. We apply Newton's second law here. So the x component of the resultant force is the mass of the particle, which is m, times the x component of the acceleration. So the m's cancel, and just like the case of a particle on a fixed wedge, the component of the acceleration down the wedge was g sine theta. Well, this was the entire acceleration for the case of a fixed wedge, but in this case it's only one of the components. We still have to get b sub y. To do that, we need to get the y component of the resultant force on the particle. So we can see that we have the y component of the weight mg, that's mg cos theta, that's pointing in the positive y direction. And we have vector r, which is pointing in the negative y direction. Now we apply Newton's second law in the y direction. The y component of the resultant force is the mass of the particle times the y component of the acceleration. For the case of a fixed wedge, we saw that r was equal to mg cos theta. That's because the particle had no acceleration in a direction perpendicular to the incline. In this new situation, r is actually less than mg cos theta. Okay, now intuitively this makes sense. We would expect the force on the particle due to the wedge to decrease if the wedge is free to move to the right. Contact between them is not as strong as the case of when the wedge is at rest. So anyway, this thing here is not equal to 0, as it is for the case of a fixed wedge. We have a net force in the positive y direction, so this vector here is a bit greater in magnitude than this vector here. So that's why we have a positive y component of the acceleration. Okay, so if we look at this equation, we see that there are two unknowns. We have r, and we have this new unknown b sub y. So we cannot solve between this equation and this equation over here. What we can do is we can connect b sub y, the y component of the particle's acceleration, to a, the acceleration of the wedge. By the way, I should have mentioned earlier that r is a constant vector, no matter where the particle is on the wedge. The particle remains in contact with the wedge, and the force on the particle due to the wedge is this vector here, which never changes. So, you know, when the particle is, say, down here, Okay, and the wedge has moved on. We have the same R acting. This vector is identical to this vector, same magnitude, same direction. Okay, that's something that we observe from experiment, and you can also prove it. Okay, the key result that we will show is that b sub y, the y component of the particle's acceleration, is equal to a sub y, which is the y component of the acceleration of the wedge. Let's look at this more carefully by referring to our y-axis here. So this is only true for the y components. Let's imagine that we project this particle onto the y-axis at right angles, of course. Let's also imagine that we pick a point on the wedge, any point at all, and project it onto our y-axis. Our y-axis, remember, is fixed. So we could just pick, say, this point here and project it onto the y-axis. Let's now consider the motions of these two projections. Well, the wedge is going to move to the right, so it's clear that this projection will move in the positive y direction. This could be the velocity of the projection, or it could be the acceleration. The particle is always in contact with our wedge. The distance of the center of the particle perpendicular to the surface remains constant. So this distance between the two projections is constant. So whatever velocity or acceleration the particle has, the wedge will also have that. If both of these are velocity vectors, well, then these velocity vectors will increase in time, but it'll always remain equal. If they're acceleration vectors, they will always be equal and will never change, actually, because we're just dealing with constant forces, so the acceleration vectors are constant. Okay, so I'll draw this vector here. This is going to be a sub y, the y component of the wedge's acceleration. I'll just make it a bit bigger so I can show it over here as well. You know, as for the wedge, b sub y is going to look like this, and both of them will have the same magnitude. So to show it over here, we just project the tip of vector A onto the y-axis. So I'll show the y-axis here. Okay, so we project at right angles onto our y-axis, and here is the y component of vector A. So this vector is meant to be the same as this vector. We could also have shown a sub y up here, actually. As a matter of fact, if we show it up here, we can see that this angle is theta. That's the angle between the horizontal and our x-axis, which is the angle of the incline. So let's say we look at this right angle triangle up here. We want a sub y in terms of a. So a is the magnitude of the wedge's acceleration, so it's some positive number. A sub y is opposite theta, so a sub y is hypotenuse a times sine theta. So now we can plug a sine theta into b sub y, and we don't have to worry about whether b sub y is positive or negative, because we have this problem set up in such a way that a sub y is pointing in the direction of the positive y-axis. A is a magnitude. It's meant to be the magnitude of the acceleration, so it's positive, and obviously sine of theta is positive. So all of this quantity is positive. So we're not going to get mixed up with signs. So now at last we can solve for the acceleration of the wedge, because here we have an equation with two unknowns, r and a. Everything else are givens. Little m is a given, theta is a given, and up here from the forces on the wedge we have an equation with two unknowns, big M and theta are givens. Okay, so to solve for a, I will replace r in this equation using this other equation. So we get mg cos theta minus r, where r is just big M a over sine theta, and that's equal to little m a sine theta. So we just have one unknown in this equation, which is a. So there we have it, a formula for the acceleration of the wedge. So just to get to this formula, I multiplied above and below here by sine theta. That's just to cancel the sine theta in this denominator. Now let's get R, the force on the particle due to the wedge, or if you like, the force on the wedge due to the particle. Its magnitude is given by big M times A over sine theta. So I'll put the big M on top and divide the top by sine theta. So we'll have big M times little mg cos theta, and the denominator remains as it is here. Now we can write this a slightly different way. If I divide above and below by big M, we get this thing here. Notice that this thing here is less than mg cos theta. Okay, because we're taking mg cos theta and dividing it by something that's bigger than 1. But remember that mg cos theta is R for a fixed wedge. So just as a reminder, we have our particle of mass m here. We have mg acting down. We have R. So imagine now that this wedge is fixed. Well, this vector here is mg cos theta. And these vectors are the same if the wedge is fixed. You see, the particle doesn't accelerate in the y direction. So the result that we get for the moving wedge makes sense, because we expect this quantity to be less than the situation where the wedge is fixed, since the wedge is moving away from the particle, if you like. As an aside, notice that if we make the mass of the wedge big M very big, make it infinitely big, well this quantity here is going to go to 0. Okay, keep everything else the same, just make big M approach infinity. All of this quantity will go to 0, so we'll be left with mg cos theta over 1. So we are approaching the value it would be if the wedge is fixed, and that makes sense. If we make the mass of the wedge infinitely big, well, the mass will not move. We will have a force on the wedge, but its mass is so big that its acceleration is 0. Now let's look at the acceleration of the particle. So that's vector b. Its two components are bx and by. We found both components. So here's the x component, g sine theta, and we can multiply that by unit vector I. So unit vector I is a vector of length 1 but pointing in the positive x direction. So its magnitude is 1. And similarly for the y component, we have by times unit vector j, where j points in is a unit vector pointing in the positive y direction. Now what is b sub y? Well, b sub y is given by a sine theta, so I'll write it like that. A sine theta, where a is given by all of this here. I won't bother plugging this in. Okay, so anyway, here we have vector b fully specified. If we want the resultant force on the particle, we just use Newton's second law, which says that F equals m times the acceleration b. So we just multiply all of b by m. We can consider the magnitude of the acceleration of the particle. We just square both components and sum them. Sine squared theta is a common factor here which can be pulled out. The square root of sine squared theta is sine theta. And inside we have the square root of g squared plus a squared. So this will be the acceleration of the particle. Let's look at the acceleration and the velocity of the particle relative to the wedge. Here is our formula for relative acceleration. You can see that it's got the exact same form as the formula for relative velocity. So here we have the acceleration of the particle relative to the wedge. That's the actual acceleration of the particle minus the actual acceleration of the wedge. Well, the actual acceleration of the particle is just this vector b. Okay, that's its acceleration relative to a fixed xy axis. And as for the acceleration of the wedge, well, we just call that a. Now let's write b and a in terms of I and j unit vectors. Well, b we know is just bxi plus byj. And as for a, Well, we can write that in terms of its x and y components. We have axi plus ayj. But we've seen that ay is just equal to by. The y components of the acceleration of the particle and the wedge are the same, so these cancel out. So you see, we only have to subtract the x components. Well, we already know what bx is. For any particle of mass m, bx is g sine theta. What's more, it's pointing in the positive x direction, so that's the x component of the velocity relative to our fixed x-axis. What about ax? Well, you can see from this diagram here that ax is actually pointing in the negative x direction. It's pointing up the incline. We could imagine a point on the wedge and consider its acceleration, which we know is to the right, is a, and look at its x component by just projecting onto our incline. So this here would be a sub x. Our angle in here is theta, so it's only a matter of multiplying a by cos theta. So we could show it here, or we could show it over here. This angle in here is theta, the hypotenuse is a, so a times cos theta. And we must stick in a minus sign because it's pointing in the negative x direction. So we have b sub x, which is g sine theta, minus a cos theta. Okay, so this formula makes sense intuitively because the particle's acceleration is downwards with magnitude bx. I mean, the x component has magnitude g sine theta downwards, but this particle, this fixed particle on the wedge, this point is part of the wedge, has magnitude a cos theta up against the x-axis in the negative direction. So we're in a sense adding the magnitudes of these two vectors. So we have two oncoming objects, the particle of mass m and a fixed point on the wedge. So the closing acceleration, if you like, is got by summing these two. So it makes sense that we have to sum them. So we get an answer that's greater than just g sine theta when we're considering the actual acceleration of the particle. So from the point of view of a fixed point on the wedge, the particle of mass m appears to approach this point with this acceleration here. So this is going to be a positive acceleration. It's always going to be positive. Okay, the particle will appear to approach the point, so it's moving in the positive x direction. So if you want, you can drop this I here, and now we have our formula for the acceleration of the particle relative to the wedge. Now let's consider the velocity of the particle relative to the wedge. Well, we apply our relative velocity formula, and I've written Vp in terms of its I and j components. So Vpx is the x component of the particle's velocity, Vpy is the y component of the particle's velocity. Similarly for the wedge. Now the particle starts at rest, so the direction of its velocity will be the same as the direction of its acceleration. So let's say this is the velocity vector for the particle, so this is v sub p. Well, here's its x component and here's its y component. The velocity of the wedge will be in the same direction as the acceleration. Okay, the wedge starts at rest, it accelerates to the right, so its velocity is to the right. So let's say this is VW. Well, VW has a y component and an x component. Well, we've seen before that the y components of the accelerations of the particle and the wedge are the same. So it's the same story for the y component of the velocity. This vector here is identical to this vector here. That's because the particles are connected. Okay, we looked at the projections before, and the projections have the same velocity and acceleration in the y direction because the distance between the projections is fixed. So these terms cancel out. Okay, so we're just left with these x components, so we can write a relative velocity vector like this: Vpx minus Vwx times unit vector I. Now the velocity of both particle and wedge are changing with time, of course, because both particle and wedge are accelerating. So if we use the formula v equals u plus at, but apply it to particle p in the x direction, we can find the velocity as a function of time. So once we know the time, we have our velocity. UPX is the initial velocity of the particle in the x direction. Well, the particle starts from rest, so the initial velocity is 0. Now we already got the acceleration of the particle in the x direction. Well, we call it b sub x. I'm just after wiping it out here to create room for the velocity vectors, but we saw that it was b sub x, and we got b sub x actually. We saw that b sub x is g sine theta. Okay, so there we have it. So here's our constant or uniform acceleration. We just multiply that by the time to get the x component of the particle's velocity at that particular time. Okay, let's get the x component of the wedge's velocity. Well, let's first of all relate the x component to VW. Well, you know, we could say VWX is minus VW cos theta. We could do that, and then we could relate VW to A, the acceleration of the wedge. Or we can do what we have here. We can use what we have here. Okay, so first of all, we'll write down our formula. V equals U plus AT. It's the initial velocity of the wedge in the x direction plus the acceleration of the wedge in the x direction times time. But the initial velocity is 0 because the wedge starts at rest. And we have the acceleration of the wedge in the x direction. It's minus A cos theta. So A we will have worked out from the previous part, the acceleration of the wedge. Multiply that by cos theta and multiply by time. And we have the x component of the wedge's velocity. Okay, so here's the velocity of the particle relative to the wedge at any time t. I've dropped this I here. Notice that this thing can be written with the t factorized out. You know, we could write it like this, and of course we recognize what's in here. This is the acceleration of the particle relative to the wedge. So again we have V equals U plus AT, where U is 0. U is the initial velocity of the particle relative to the wedge is 0. So there's our U, and here's our A times T. Now let's write down the velocity of the particle. Well, here is V sub x. Okay, that's our Vp sub x. That's g sine theta times t. So that's that term there. And we want Vp sub y times j. Okay, to get the y component of the particle's acceleration, you know, we just get the y component of the particle's acceleration. So sorry, we want the y component of the particle's velocity. So we need the y component of the acceleration, which of course we multiply by t. Okay, so it's V equals U plus AT, where U sub y is the initial velocity of the particle, but that's 0 of course. Okay, because the particle starts from rest. So we need B sub y, but we know that B sub y is just the same as A sub y. And we saw before that B sub y is A sine theta. Okay, so here's our formula for the velocity of the particle at any time t, so we just plug in for t. We also need the acceleration of the wedge, plug in for that, and the angle theta. Right, let's look at the velocity of the wedge. Well, again, we just use V equals U plus AT. We want the initial velocity of the wedge plus the acceleration of the wedge times time, and the initial velocity is 0. So we have the acceleration of the wedge times time. Well, we just call the acceleration of the wedge A. We don't put in the W. We know we referred to it as A earlier. So we just multiply A by T. We could of course write VW in terms of X and Y components, but we don't have any need to do that because we know the direction is to the right. Let's look at this example here. All the surfaces are smooth. Little m is 3 kilograms. Big M, the mass of the wedge, is 4 kilograms. Theta, the angle of the incline, is 45 degrees. Now we could go through the method of the previous part, but I'll just plug into this formula that we derived. So plug in for little m, big M and theta. We find the acceleration of the wedge is 3g over 11 meters per second squared. Now let's consider the acceleration of the particle relative to the wedge. So we saw previously that if we work out AP minus AW, the y components cancel out. So the y components were in this direction, perpendicular to our incline. So we end up just having the x components. As a reminder, the y component of b is this vector here, b sub y, that's equal to a sub y. Okay, these were the same. Anyway, the x component of the acceleration of the particle we call b sub x. We saw that b sub x is g sine theta. In our example, theta is 45 degrees. Then we have to subtract the x component of the acceleration, and we saw that the x component of the acceleration is minus a cos theta, where theta is 45 degrees in this case. Okay, so it's pointing in a negative x direction, that is up the incline. So in general, we just use this formula here, g sine theta plus a cos theta. So we have to multiply a, which is 3g over 11, times cos 45, which is 1 over root 2. Okay, with a common denominator of 11 root 2, the acceleration of the particle relative to the wedge is 14g over 11 root 2 meters per second squared. So as a reminder of what that means, if we imagine point on our wedge, a fixed point on our wedge, well, the particle will appear to accelerate towards this fixed point, that is in this direction, in the positive x direction, with this acceleration. And you can clearly see that this acceleration is obviously greater than the actual x component of the particle's acceleration. That is the particle's acceleration relative to our fixed x-axis. In part 3, we want to find how far the wedge has travelled when the particle has moved a distance of 1 meter down the inclined face of the wedge. So to a fixed point on the wedge, we have the acceleration of the particle down the wedge. It's given by this thing here. And the particle moves a distance of 1 meter. Okay, so we have the distance and we have the acceleration of the particle as seen by a fixed point on the wedge. So one way to do this problem is to find the time taken for the particle to move a distance of 1 meter down the wedge. So we have its acceleration relative to the wedge. Distance, initial velocity is 0, particle starts from rest. So here's the relevant formula we need for linear motion with uniform acceleration. U is 0. Okay, we plug everything in, and to 3 decimal places t is 0.476 seconds. Now we can answer the question of how far the wedge has travelled. We have the acceleration of the wedge from the previous part. We have the time of travel for the wedge. The initial velocity of the wedge is 0 because it starts from rest, and we want to find s. Okay, so in the time taken for the particle to move 1 meter down the incline of the wedge has moved to the right a distance of 0.3 meters. Now as an aside, let's consider the speed of the wedge and the particle at the time t equals 0.476 seconds. So working this out, we get 1.274 meters per second. Now let's consider the speed of the particle. Its initial speed is 0, and we want its final speed. I'll call it Vp. That's its speed at t equals 0.476 seconds. So here's its acceleration vector. We called it b previously. We know that b sub x for any particle is g sine theta. Okay, so we're looking at its x component. It's g sine theta, where theta is 45 degrees. So sine of 45 is 1 over root 2. What about b sub y? Well, we saw that b sub y, this vector here, is the same as a sub y. Okay, so here's b sub y. A sub y is a sine 45. So that's a over root 2. Okay, so we've a over root 2, or the acceleration of the wedge is 3g over 11. So we have to divide 3g over 11 by root 2. So we get 3g over 11 root 2. Okay, so that's our acceleration vector. We want the magnitude of this vector. So we have to take the sum of the squares of the components. We get a g squared from both squares, and the square root of g squared is g, so we can take that g outside. Okay, we've g squared factored out. The square root of g squared is g. Squaring 1 over root 2 gives us a half. Squaring 3 over 11 root 2, that's going to give us 9 over 11 squared by 2. Okay, so that's what we want for our acceleration. Alright, so we now have the velocity of the particle at this time, 0.476 seconds. It's 3.42 meters per second. So the particle is moving in the direction of the acceleration, which is b, this vector b. It's not vertically down. So in 0.476 seconds, it will have moved in this direction. Well, its speed will be 3.42 meters per second. So its velocity vector is in the direction of vector b. Finally, let's consider the velocity of the particle relative to the wedge. Well, we saw previously that when we calculate Vp minus Vw, the y components cancel out. The y components of the velocities are the same, just like the y components of the accelerations are the same. So we only have to look at the x components. Okay, so the velocity of the particle in the x direction is the initial velocity in the x direction, which is 0, plus the acceleration of the particle in the x direction times t. So it's just v equals u plus at applied. And similarly for the wedge, so we saw all this before. The acceleration of the particle in the x direction we call b sub x. This is multiplied by, we take out the t. What about the acceleration of the wedge in the x direction? Well, if we go back here we have it. It's minus a cos 45, which is minus a over root 2. So we're going to get minus a over root 2, or plus a over root 2. We know that b sub x is g sine theta, where theta is 45 degrees. A for our problem is 3g over 11, so we divide that by root 2, so we get 3g over 11 root 2. And the time that we're interested in is 0.476 seconds. So we get this large value, 65.37 meters per second. Let's look at a similar example. So we have a particle of mass 3 resting on a wedge of mass 8. So you can go ahead and get the acceleration either using this formula or going through the methods of what we did previously. Little m is 3, big M is 8, theta is 30 degrees. Okay, I'm going to leave our answer in third form, so I'm multiplying above and below by 4 here to get 3 root 3g over 35. We are given that the wedge moves 3 root 3 centimeters in t seconds. Before going any further, let's find out what t is. The initial velocity of the wedge is 0. We have the distance s, so we use this formula to find out what t is. U times t is 0, so we see that t is 2s over a, and we have to take the square root. So 2 times s is 6 root 3, and here's a. Okay, we can cancel the root 3's, divide 6 by 3 to get 2, multiply on top here by 35, and underneath by 35. So we get 2 times 35 is 70, and we just have g underneath. By the way, I forgot to convert s into meters. S is given in centimeters, so we need to divide this by 100. So everything on top is divided by 100, so we could multiply above and below by 100. So we're going to get 100 g underneath. Okay, so I'm multiplying above and below by 100 to cancel the 100 in the denominator on top. Okay, so in the time that the wedge moves 3√3 centimeters, the particle is moving down the incline. So the wedge gets to here. Okay, it should look like this, and the particle has obviously moved down the incline. So we're interested in the ground that the particle moves down the incline. Okay, so we're interested in the velocity of the particle relative to the wedge. So we can imagine a fixed point on the wedge, and we want to see the velocity of the particle relative to this fixed point on the wedge. Well, it's not the velocity we want actually, but the acceleration of the particle relative to the wedge. So again, like before, we saw how to do this. We saw that the y components cancel out, and we're just left with the x components, where the x-axis, the fixed x-axis, is parallel to the incline, and downwards is positive. The acceleration of the particle relative to the x-axis is we call b sub x, where b is the acceleration of the particle. Now we want the x component of the wedge's acceleration, a sub x, or aw sub x. Okay, this is 30 degrees, so we know what that is. The x component is a cos 30. Okay, I need to emphasize, of course, that it's negative. Okay, it's pointing in the negative x direction. The positive x direction is down the incline. Okay, so we minus a cos 30 here. So we minus a cos 30, so we get plus a cos 30. So we've seen this before. B sub x is g sine theta. Our general formula is g sine theta plus a cos theta. Okay, for this kind of situation of one particle on a wedge. Okay, sine 30 is a half, cos 30 is √3 over 2. √3 by √3 gives us a 3 on top, and 2 times 35 is 70. So we get a common denominator of 70. We have 35 plus 9 is 44. We end up at 44g over 70, which is 22g over 35. Okay, so we have everything we need now. The initial velocity of the particle relative to the wedge is 0. It starts at rest. We have the time. Okay, and we want a distance. So this is the distance traveled by the particle down the wedge. So we get 11/50ths of a meter, and if we want that in centimeters, we multiply by 100. So that's 22 centimeters. So the particle moves 22 centimeters down the wedge.